Okay, now let's go on to a problem that deals with the actual stability. We have a reaction here in which a strong base is reacting with this molecule here, and we want to know which one of the hydrogens is most likely to take. So I'm going to fill in the hydrogens here in this line angle structure. We know that when carbon needs to always have 4 bonds, so we'll just fill it in. These should have a total of 3. And this side's just the same thing as the other, since it is symmetrical. And since it's symmetrical, all these hydrogens are mostly identical except the ones in the middle. Let me draw that axis of symmetry with the dashed line. So we really only have 2 types of hydrogen. We have type 1 over here in an end and type 2 in the center. So really we only have 2 options into which one of these hydrogens are going to react. Now to actually figure out which of the 2, we need to figure out which forms the most stable product. They both should form water because you have a hydrogen reacting with an OH. Obviously H plus OH is H2O. Now the question is which one is preferred. So we can have, if we drew out our negative charge attacking a proton, that proton obviously is positively charged, and when we break a neutral charge and make a positive, that means we get left with a negative. In other words, this oxygen donates its electrons to the carbon. Now we can do the same thing with hydrogen number 2. Again, it's a proton we're taking, so it's positively charged now, and it ends up going back and donating its electrons to make a negatively charged carbon. So we'll draw the product. Obviously, both cases we get water, but drawing out the same skeleton again. Let me see if I have it saved. No, I do not. So we will redraw the skeleton here and decide which of the 2 is the most stable based on resonance. To decide which of the 2 is more stable, we usually go by which of the 2 has more resonance structures, because that forms a hybrid that is basically sum of all the resonance structures. I could show that too at the end. Let me go ahead and show the 2 options. So in form, when we take hydrogen 1 at the end here, we get the negative charge here, and when we get the hydrogen 2, we get the negative charge in the center. Now, which one of these is going to have more resonance structures? Let me move him here, and let's figure out how many resonance structures we can have. So this is, if we take hydrogen number 2, now let's move around its resonance structures. Let's fill in our lone pairs as we did before. As we know, we have oxygen with 2 lone pairs when it's in this state. And let's try to take that negative charge, which is also a lone pair. Let me just get rid of it for now. Okay, so we can have, maybe we can move this to the center here, and we can kick off one of these pi bonds and make another lone pair. And that way we can share the negative charge with this oxygen. But since it's symmetrical, we could technically do the same thing on the other side. So we can have another 2 resonance forms. So let me draw the result. We have same thing going on twice. We turned this into a single bond. Let's say we kept this one the same for now. And we created a new pi bond here following the red arrow that moved that lone pair into a pi bond. But we also kicked off one of the pi bonds into a lone pair. So here we have a negatively charged oxygen. And we said we can do the same thing to the other side. So we can do the same thing. It's just the mirror image of this original one. So I will just move things around a little bit as to represent that. So we moved it here. This here now has a negative charge, and this here is neutral and has another bond. So you can have a total of 3 resonance structures. Now, in the option 1 here, we can try to move that lone pair as well. Let's see. So let's see any resonance structures we can move. We can do a similar movement, have this turn into a bond, and we can kick this out here. But the difference is we can't move things 2 over, because that would be we can only move it to the neighboring, so we can't share with this oxygen over here. Oop. Not an option, that oxygen. So we only have one more state that we can create. The other resonance structure would look like this molecule here. And there's a double bond here now. Another thing you can do to keep track of your charges is count your hydrogens. That always helps to figure out what the difference is between the two. Like here we had originally 2 hydrogens. So obviously you need to keep that carbon happy. If it doesn't have that pi bond anymore, now it has a bond. Sorry, if it doesn't have that lone pair anymore, now it has a bond to keep up and make sure it's still in a state with a charge or neutral. Okay, so now which of the two is more stable? To come to the conclusion that which one of these is correct, we actually have to decide which one has the more resonance structures. We said that 2 has the most, so we want to take one of these hydrogens for this reaction because the product is more stable with more resonance structures. A reaction will always follow the more stable product. So we could also say that this hydrogen is more acidic, more reactive, and this hydrogen number 1 is more stable and less reactive. Looking back, the reason why these are so stable with more resonance structures is because they actually exist in a state hybrid to all of these. So basically, if we talked about this molecule, we drew the resonance structures before, it would actually look like halfway in between both. The charge would be shared by the oxygens. We represent that with dashed lines, and they'd both be partial negative, partial 1/2 charge. That's much more stable than one oxygen with 1 charge. Anyhow, just to review, use your robes to describe the major and minor contributors based on complete octets, number of bonds, molecules that are the most electronegative holding charges, and charge separation. We want negatives and positives near each other and negatives far apart. Thank you for watching. Let us know if you need any more help in the comments.